All right. Well, thank you, Paul, for the invitation. It's nice to see everyone. And I'm delighted to be here. As Paul said, I work for D-Wave. I'm on the benchmarking team. We're a small group inside the company that's pretty much charged with just evaluating performance of whatever gets put in front of us. And so a lot of that is prototype hardware systems. We're giving feedback to the hardware development teams, and a lot of it is the software. Now we've got the software stack on top. So benchmarking is what we do, and this is really a talk about some recent work along those lines. So basically, I want to talk about a new metric that we've developed, which we're calling quantum utility, and it's divided into milestones that are sort of components of that we can build up and get to full quantum utility. And I'll present a little example or a large example of a benchmark test that we performed recently on one of the Advantage QPUs. And interestingly, not only usually we just think of benchmarking as telling you what happened, what you observed, but this actually this approach allowed us to do a little bit of model building and try and come up with explanations for the performance patterns that we were seeing. And so there are some new intuitions that allow us to characterize QA performance, which means predicting the circumstances under which it might do better or worse than classical computation. So that's what this is about. And in particular, I'll be talking about the Advantage 4.1 QPU. That's the flagship one that's in Burnaby. It was launched in 2020. Is that right? The Advantage system was launched in 2021, but this one is a little bit later. It wasn't one of the originals. And I'll also talk a little bit about the Advantage 2 QPU, which is the next generation machine, has the Zephyr topology that's going to be launched sometime either later this year or next year. And I think everyone probably knows that this is not a gate model approach to quantum computing. We use this Hamiltonian-based approach, which is a better match for solving optimization problems. So this new metric, the idea is to try to get to capture QPU performance as experienced by the user. And on the right-hand side, because these are optimization problems and heuristics, there's sort of three dimensions of performance that we can look at. We generally, with heuristics, have the idea that if you invest more time, more effort into the computation, the solution quality will improve. Here we have energies going down with time, and here's a different input, and it behaves differently. And usually this scaling performance, solution quality and time is highly dependent upon the inputs. Sometimes it's good, sometimes it's bad. And so we're also looking for robust performance in the sense that the solver doesn't require a lot of input specific tuning that would kind of kill the whole point if you spend all your time tuning. If you spend a lot more time tuning to solve the problem than you spend actually solving the problem, then that's kind of a drawback to the whole approach. So and because we're trying to capture the user experience, we don't want to just measure anneal times. We know there are overhead costs that the user experiences, and we want to incorporate those overhead costs when reporting the computation times. So that's why we come up with these ideas of milestones. We think about all the overhead costs associated with quantum annealing, problem transformation and minor embedding and shipping the thing across the internet. And, that adds up and, can create, a considerable overhead obstacle to good performance. And so what we want to do is focus on specific subsets of overheads and measure them carefully and evaluate how the QPU is performing with respect to subgroups or pieces of these overhead costs. So the first three milestones that we've identified is milestone 0 is just the pure anneal time. You measure against classical computation when you're just comparing anneal time to basically classical solve time after the input is read and before the outputs are written. So that would be milestone 0 if we could show better QPU performance in that under that in that condition in that case. Milestone 1 includes chip access time, which is programming time and readout time that happens to move the. It's kind of analogous to I/O, but it takes a lot more time than classical I/O. So that's access time. And then the third milestone is we're going to consider an indirect cost of minor embedding. We're not in this case going to actually measure the computation time for minor embedding, but we're going to look at the differential in problem size that classical solvers that can solve the original unembedded problem compared to the quantum solver that has to deal with a larger embedded problem. And we'll look at the differential that would be due to just, being able to solve smaller inputs for classical. So with respect to milestone 1, I'm actually not going to go into it, not to address it. There are plenty of papers in the literature where that kind of test has been performed. And cases here and there where the QPU has been outperforming classical solvers since really well, in one case, the D-Wave 2, but that was kind of because there weren't good solvers, classical solvers back then. But I've got a citation list at the end if anybody wants to follow up on those. So what is milestone 1? This on the left here is a diagram that I just made for illustration purposes. This is not real data. Your mileage may vary. But basically, we have this idea that programming time, on the Advantage system, it was about 15 milliseconds, and my diagram shows 20 milliseconds. But that's a big time in these problem domains that we're interested in, and it's just sitting there programming the chip, and then boom, 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 you can get a lot of anneal readouts, and each dot here in my diagram, the width of a dot is about a half QPU time and half readout time if you set them both to about 200 microseconds. So, the actual anneal times are very short. And, so you can get a lot once you've gotten past that programming time. We're going to consider the possibility that there are multiple programmings for one input. Just as a heads up, you can use different programmings to change parameters of the physical representation. And so we're doing that a little bit. But in this example of mine, in 100 milliseconds, the quantum annealer was able to turn out a sample of 200 solutions, random or independent solutions. In comparison, a greedy solver, it starts with a random input and rolls downhill till the nearest local minimum, is also very fast. Boom, boom, boom. It could bang these things out, and it doesn't have programming time. And so we can imagine a greedy solver, in this example, giving you 165 solutions in 100 milliseconds. But they're not as good because all it's doing is finding the nearest ground state. And then simulated annealing can kind of work both ways. It has a parameter, which is the number of sweeps. It's the number of main loop iterations, allowing it to converge. And if you only need one solution, then you can have a high number of sweeps and let it go all the way to 100 milliseconds, and it will just return one solution, but it's a pretty darn good solution. Whereas if you need 10 samples in that same time, it can only use 1/10 the time per sample, and they're going to generally not come out as good quality solutions in that case. So these are the parameters that we're going to look at when developing these tests. And here are some typical QPU times: 15 milliseconds programming. When I wrote this slide, it was between 2 and 2,000 microsecond anneals, but now the current systems are going down to 0.5 microsecond anneals. And, you could have one readout or many readouts. They are about 250, 240 microseconds per on current systems. So the idea behind milestone 1 is to evaluate QPU performance when we're measuring access time, not anneal time. And the second milestone has to do with this indirect cost of minor embedding. You get a problem that's defined on a general graph, G, but of course you have to minor embed it into the Pegasus architecture, the Pegasus connection topology that is a physical representation of the qubits in the chip, the qubits and couplers in the chip. And what minor embedding does is it maps each node of the original graph, here's a big node highlighted, onto what's called a chain of qubits in the physical graph. And it doesn't have to be a chain, they could be tree-like, but in this case, the single node here got mapped into two nodes here that are connected by a chain edge. This is, you know, a strong ferromagnetic coupler that tries to ensure that they both end up with the same solution. You know, when the answer comes back, that the two qubits have the same value, so that you know how to map it back. If they're not, if they don't have the same value, that's called a broken chain, and there are mitigation techniques that can be applied. So, but the point is that what happens when you're minor embedding, unless the original graph is a subgraph of Pegasus, is that you're going to get a bigger problem when you do this. The number of nodes is going to expand, and because you're basically in many cases trading edge degree for high edge degree for low edge degree, but more nodes. And so you have to use more nodes to represent dense edges, is kind of the intuition behind that. Here, this graph is, the embedded graph is about 30% higher than the original graph in terms of number of nodes. All right, so those are the properties we're trying to evaluate here. And we basically developed one test, one big experiment that gave us the results for both of these milestones. So in particular, our inputs, we developed 13 different input classes and generated 25 instances for each class. 5 of these are native. They're defined directly on the Pegasus graph. So both the physical and the logical graphs are identical in that case. And 8 of them are embedded. They have a logical version that's different from the physical version. And one thing I'll say is that, you know, we have a lot of ideas for what inputs to use, and we did pre-screen these for hardness, in the sense that if we learn that classical solvers, simulated annealing and greedy in particular, can find ground states in less time than the programming time, the 15 milliseconds, then there's kind of no point in performing the test. We know from the get-go that the classical solvers will just solve the thing while the QPU is still programming. So we'll concede that those problems are too small or too easy to be solved. They could be solved easily classically, and we didn't include them in our test. So the only inputs in our test are inputs where we didn't do any prior tests on the QPU. We just checked whether basically the greedy and the simulated annealing solver were appearing to solve to optimality by multiple cases of the same lowest energy coming out, and we omitted them if that was the case. And if there are questions at the end, I can talk about what we ended up omitting. But what we ended up with was 5 native inputs and 8 inputs that are after embedding can be used for milestone 1, and they are all defined on a physical graph, and we can compare the performance of solvers on when they're running this, when they're reading the same inputs that the QPU is reading. And then in milestone 2, we took the 8 embedded problems and we compared performance of classical solvers on the pre-embedded version against quantum solvers on the post-embedded version. We used 7 classical solvers. 2 of them are implemented on GPU, and so they solve the native Pegasus graph and have some optimizations embedded to sort of make that, to maximize the efficiency of the parallel GPU computation. We use this, it's a simulated annealing solver, and we have a lot of parameter settings. One of them was one solver was basically set just to dive down to optimal as fast as possible, and the other was set to broaden out and get diverse samples. So there are 2 versions of the same solver under different parameterizations. And then we have a bunch of solvers that read general graphs, and they're implemented on CPUs, random CPUs greedy descent, a type of greedy algorithm, simulated annealing. This is the NEAL solver that is available on the website. Parallel tempering solver that is implemented on a CPU, and another one, this is actually parallel tempering misspelled, implemented on a GPU. But so this is a GPU solver that reads general graphs, not Pegasus graphs. And so what we're going to do is ask each solver on each input instance to return samples of size 1, 10, 100, and 1000 within time limits of 20 milliseconds up to 1 second in these increments. So if we ask it to, if S is 1,000 and S and T is 1, that means 1,000 samples have to be returned in the 1 second. So each combination of S and T is called a scenario. That's a test scenario. And another point I will mention is that we're looking for robust performance across all these different inputs. And so we're looking for solvers. So we're paying careful attention to the tuning that goes on. And we adopted what's called a fair test policy in optimization methodology papers, which basically says that, all the solvers have to get the same amount of effort. And so we used default parameters settings, just constant values as much as possible. And when it was really necessary, we, in some cases, if there is some auto tuning that goes on, with respect to a certain input, the solvers, the classical solvers are allowed to do that, but that's included as part of the runtime cost of the computation. So we're equalizing the tuning with respect to these time limits in these scenarios. So here's a quick look at our inputs. The first 5 are defined on the Pegasus graph. And these are all basically graphs found in the literature on quantum speedup, which sort of attempts to identify inputs where you can find a scaling difference between classical and quantum annealing at small n, of course, because it's empirical. And so these are more or less, intended to have structure that can be hard for both classical and quantum solvers to solve. So these are challenging inputs that are put directly onto the quantum chip, and the reason for including them is because they're believed to be hard and have been demonstrated hard in different contexts. The next 1, 2, 3, 4, 5 inputs are random inputs from different papers. 3D lattices are the, it's a three-dimensional grid. They're technically defective lattices. Couldn't think of the term. So if there are qubits missing in the graph, then the corresponding node in the 3D lattice is not missing is missing as well. So these use basically chain length 2. So you get about you get a 3D lattice about as half the size of the number of qubits you have. This is BPSP is the binary paint shop problem. There's a paper by Volkswagen describing this problem. And our generator is slightly different, but is inspired by that work. D-reg is deregular graphs of degree 3. And so every node has degree 3. And SOC, these are social network graphs that are used in certain kinds of social network analysis. And we have signed graphs and unsigned graphs according to whether the nodes have positive and negative weights or not. They're basically what are they called? Friendship graphs in a social network that labels edges with respect to positive and negative encounters. And then we have 3 cliques, 3 types of cliques: Sherrington compacted graphs, a graph used in network communications, something multiple access. It's about, splitting up your
code division.
Yes, code division, multiple access graphs defined on cliques, and DAI graphs, and these used an AI approach to find to learn hard inputs from a bunch of other graphs, that were kind of put together. So these were proposed by a colleague of mine. The clique graphs were embedded by the clique embedder. The ones in teal here were embedded by our heuristic minor embedder, and the ones on top don't require. Well, I guess 3D lattices weren't embedded by minor. They have being a regular lattice structure, they have a custom embedder, and the ones on top don't require embedding. All right, so we used we ran all these inputs and all of these input classes for all these different scenarios. And to analyze the outputs, we used a rank-based approach, which I'll describe here. Across the top, you see 3 different sample sizes: S equals 1, S equals 10, S equals 100, and S equals 1,000. All of the images on the page are for half-second computation times, 0.5 seconds. And you see results for 3 inputs. The NAT1 input is native inputs plus minus 1 defined on the Pegasus graph. 3D lat are the 3D lattice problems. They also have plus minus 1 on the weights. And then n equal 175 here is the smallest, these shared and compacted graphs, also with plus minus 1 on the weights. So in this case, we have 3 identical weighting schemes, but 3 very different graph structures. And what we did in each scenario, we took 25 inputs, and we took, there's no way to find the ground state we have no way of knowing what the ground state is on most of these problems. They're much too large. So what we did was take the best solution by any solver in the test at any point in the test, and we called that the reference state. It's like a fake ground state as best we can do. And then we looked at the relative error of all of the other solvers in comparison to that representative, the AirSat's ground state. And so 0 is perfect. You're matching the best solution. And over these 25 inputs, these are empirical cumulative distribution density plots that show performance on all 25. So over here is the worst that each solver did in this batch of inputs. In the middle is the median performance, and over here is the best case performance for each solver. And we put these on a log linear scale. It's a special kind of log scale that transfers back to linear near 0, so that we could get a good look at the lower curves, the curves in the lower parts of this graph. So for example, then on these NAT1 problems, we're looking at which curves are below which other curves, and the QPU is in blue. So we can see that in all 4 scenarios, the QPU is returning better inputs. The blue line is completely below the others, except for this case here where there's a little bit of a tie. And however, on the sure.
Quickly remind me what sample size means. This S parameter, what does sample size mean?
Oh, so it's how many inputs you're going to, you want a sample of 1,000 independently selected inputs. But what we do with the runtimes, like if you have a half a second in hand and you want 1,000 inputs, well, several of these solvers, greedy and random and the QPU, are going to give you a bunch more than you ask for. They're going to give you, 3,000 outputs. And so to do the analysis here, we'll take the best 1,000 of those 3,000 outputs and this is reporting the median of the best 1,000 of all of the solutions that were available at this runtime. Okay, so the sample 1, the median of the sample is the same as the min of the sample. So if you're looking at just simply the best single solution you can get in a half a second of runtime, you would look in column 1. But if you're looking for a good sample of 1,000 inputs in that same runtime, you'd be looking over here. So a win means that the a line is completely below the other lines. You can tie for a win if you and if one solver and another solver are both winning on at least half the inputs, then they have tied. That's what we mean by a tie for the win. And was there a question? No, okay. And we're also going to look at fails. We you'll see on the right that not all the lines are here. And this is because there are some solvers that just can't return 1,000 inputs in a half a second. That's just not enough time to finish the mission, to finish the task. And so that would be a failure if you can't return the number of solutions needed within the requested runtime. And you'll see, or maybe you won't, it's not obvious, but parallel tempering in both of its modes was most often likely to fail. And the classical solvers also tend to fail on the really large problems and the really short runtimes. Not too surprising. So what we're going to do is look at all these scenarios and count up the winners, count up the losers, and see how the different solvers did. More questions? Are we good? All right. Milestone 1.
I think I should ask a question now. So the reason you threw away parallel tempering and other things for this S equals 1000 is because of correlated outputs if you were to try to get more outputs out of the algorithm. But D-Wave outputs are also correlated. So out of 1,000 solutions that you get, there are some correlations between them.
Well, so there's a difference. The code has a specific place where there's input and where there's output, right? And yes, we could have modified the code to say, remember the last 3 inputs, but they're implemented in such a way that they're supposed to be returning independent runs, the results of independent runs. Yes, there are correlations in the quantum system, but there are also there can be correlations in the classical systems as well, if they always always take the same track or something. So we're kind of going according to the code, what it's trying to do in terms of starting with a random instance and then improving it as best it can in the time given. And in that sense, it's just a half a second to return 1,000 solutions to a problem of size 5,000 nodes. There's just not enough time to get all. You can get what's the best PTC did. It can return 100 solutions in a half a second, but it just can't. There's just not enough time per solution to come back with 1,000. So that counts as a failure. So I guess what you're saying is. What we could say is just run it to return one solution and take the last 1,000 solutions that it provided in sequence where we know they're correlated. Yeah, that's possible, but there's not even a claim of independence there because we want each sequence to be a true sample that starts fresh with a random start, I guess is the way to think about that. Does that make sense?
Sure. Thanks.
Okay. Yeah, bring that up again. I can talk some more about things we tried. So here's milestone 1, the results. These again are all of the solvers reading the same physical inputs. If it's a logical solver, it can read Pegasus inputs, and so we just give it the compiled version and not the logical version in this case. And we're measuring QPU access times. And we asked for each of these scenarios, there were 13 inputs being tested on how many of those inputs did the QPU win or tie with classical solvers. And the answer is nearly all of them, right? in all of these, there was like one input in 3 scenarios, there was one input where one of the GPU-based solvers did better. But in most of these cases, 99% of all the individual tests, the QPU is winning. And
I think on the previous slide, sorry, so just to clarify, to make sure I've understood, this does not include those instances where the classical solvers were finding a solution quicker than the overhead time or the programming time or something, which you mentioned earlier on. This
right. We those inputs were not even in the tests. We could tell from the get-go that if an input is really small, it'll, the classical solvers will, they'll just solve it. And so if these are all inputs where it took at least, in the test, it took at least 20 milliseconds for classical solvers to find ground states. They couldn't find ground states in 20 milliseconds of computation time in the median
does
case.
that represent a significant fraction of the events you were randomly generating, or is it a detail?
Oh, it's like, how big is a hole? I mean, we can generate all kinds of inputs that are small, and even for these, we needed it to get big enough for that. And we were, in all cases, making the largest input of the type that we could embed or fit onto the QPU. So if they're small, it's always the case that, that they're easy to solve. And so we're looking for inputs that are both small enough to fit on the QPU when embedded and large enough that this timeline, this lower bound computation time is met. And the inputs we rejected are ones that, are too small, because we can run them bigger, and we can see that classical times will take more time later, but the largest embedded size we could put on the chip is still too small.
Thank you.
Does that make sense? Yep. Okay. So all of these inputs have the property that we predetermined that it takes at least 20 milliseconds, the minimum, programming time, basically imposed by programming time, to solve optimally. And whether or not the QPU, they are solved optimally after that, well, that's kind of the point of the test, is to find that out. Okay, so let me talk about milestone 2 and the logical inputs then. So this is milestone 2, and we're only looking at the 8 inputs where we have a classical solver solving the original problem and the quantum solver solving the embedded Pegasus problem. And we ask how many times did the QPU win in this case. And as you can see, the difference between getting to small, it's not as successful. There are places where it wins. And there was one input amongst the logical problems where the QPU did very well, except for the case where you need one sample in 1 second. Otherwise the QPU won. And then there were 2 inputs where the QPU succeeded when the number of samples is high and the runtime is low. These empty spots here are places where we could, by arithmetic, tell that the QPU can't solve them. The QPU can't, because of access times, and readout times can't solve these as well. For the most part, the classical solvers, nothing could do this. There were a couple of GPU solvers that could find outputs, in these cases here. But these are kind of just beyond range of all of the solvers in our tests. Really, really high sample times. Returning 1,000 samples in 20 milliseconds is just out of the question for all the solvers that we tested. That is the way to interpret that. But you can see that in cases where computation time is smallerish and sample sizes are higher-ish, giving you less time for sample per sample, are places where the QPU does better. Okay, so let's talk about these fails. Similarly, I don't want to go into details too much, but it was the case that the parallel tempering solver most often failed. This is the average number of solvers that failed in each scenario. And the GPU-based solvers never failed. They always were able to return solutions in these times we tested. But the main point here is that the patterns of times where you're more likely to see classical solvers just can't keep up are similar to the pattern of times when the quantum processor is doing well. So large inputs and small computation times, oops, I'm sorry, going backwards, are bad for classical, but somehow good for quantum. Think about that, because that kind of was disconcerting when we first observed this about a year ago. And so what would explain the idea that classical solution quality gets worse if time per solution is small, and it converges faster when n is small and slower, well, we understand that, and it's worse when it converges worse when n is large. And I'll say, you know, this makes sense. If you understand how these heuristics work, it needs more time on bigger problems, and it's going to do less well if you give it fewer, bigger problems and less time. But why would quantum solution quality be opposite? And it's not exactly opposite. There's less dependence in quantum solution quality on T over S. It doesn't actually depend too much on N. But the fact is it's getting better when N is large. And so here again are our three plus minus one problems. Cliques, the smallest ones in our tests, 3D lattices, the largest logical problems in our tests, embedded problems, and that one, a native problem. And basically these are relative errors in the minimum now, not in the median. So they're slightly different, but they give a clearer picture. And we have in brown, and we're looking at all the different runtimes now. And this blonde region here is the range of our tests. So we went from 20 milliseconds up to 1 second in the test. And those are the times captured in the blonde region here. And I think I'll start over on the right. It's easier to explain here. The classical solvers sort of form a Pareto frontier according to work versus a solution quality. And up here you see the random solver. It basically picks a random solution, doesn't do any work, and just returns it. And it's giving you the worst solutions, as is right. The greedy solver takes a random solution, rolls downhill to the nearest local minimum, and returns that. So that's a little bit more work, and it's giving you better solutions. And then simulated annealing, we have the ability to change that. The thing about random and greedy is they don't have any parameter. You don't do more work. When you have more runtime, you just take more samples. And so what these two solvers are reflecting is the benefit of taking more samples rather than doing more work on the problem, which, most people would say is pretty slim. By comparison to the simulated annealing solver, which you can set that parameter and you can increase the total amount of work, to match the runtime basically. And so this is the effect of having that num sweeps parameter on improved solution quality. And then down here in this problem, these are the quantum samples. And let me just say, you should try not to read anything whatsoever into the shape of this convergence curve, because one, it's access time. And so it's highly, if you're thinking about convergence as a function of anneal time, the actual work rather than sampling, well, access times just completely distort that. So you're not actually seeing, you need to recast these in terms of anneal times, which are all, somewhere over here in terms of total time they would take. And also in our test, we had these default parameter settings, and we didn't see very much variation with anneal time. And so the default setting here actually uses a constant anneal time through just about all of this. So this is really what you get from samples from a QPU, not from increasing the anneal time. So, but we can see that on the very large problems, the quantum processor is outperforming this Pareto front of classical solvers. On the smallest problems, the opposite is true. The random solutions are chugging along, but we can see the greedy, is it takes less time to get started, and it's converging quite quickly down to what we believe must be the optimal states because they're being found so consistently. And simulated annealing in this case, it does have some overhead to get started, but then it drops down pretty quickly, whereas the quantum processor, kind of doesn't change. I mean, in terms of it doesn't get any faster because of programming time, and it's kind of sloping the same way. I will say though, on these Sherrington-Kirkpatrick graphs, these are relatively small problems, and we can see that this is probably ground state. And this next, you can see these horizontal striations. That's the first excited state there, the second best state. And then we have the third best and fourth best and fifth best. So even though we're talking about a problem space of 2 to the 175 in terms of possible solutions, all of these solvers are getting within like fourth, fifth best of ground state here. Over here on the big problems, we have no idea where the ground state is. This just happens to be the best solution found once by the quantum annealer. So this is the sense in which, arguably, even though they met our criteria for hardness, these are still pretty easy problems because all of the classical solvers are finding ground states within the time range of our test. And then in the middle, we have the 3D lattice problems, which are, midway in between. And we can see this was exactly the case where the quantum annealer did well on when the quantum annealer outperformed all of the classical ones when runtimes are small, but not when the time per, when you can use a full second to get one solution. And so you can actually see this transition in this input that is reflected in the places where the quantum annealer won on this problem. Are there questions about that? So we can see that as problem size increases, the quantum solver is getting relatively better. Would anyone care to hazard a guess as to why that might be? No? Okay. Well, we realize, okay, you're speaking for the group, Paul, is that right? It's because of, I guess this is all the stuff I just said. We understand why solution quality would degrade with increasing problem size at the same computation times. We go from small problems to big problems, and you expect solvers they have each in the main loop, they have the search space is getting much, much bigger. The time per sweep is constant here, and yet because the problems are bigger, they're going to need more. The total time is constant, but they're going to need more time for that iteration, proportional to n plus n, pretty much. And so each iteration, each sweep takes more time, and they've got the same amount of time, so they can perform less sweeps per unit of time. And that would completely explain it. Both explains why the start times get higher, and why convergence is slower on big problems than it is on small problems. But the quantum processor is different because it's not it's not classical, and so it's not searching that state space step by step. That's kind of the whole premise of quantum computation, is it's representing the full state space using superposition in a single qubit state, an entangled qubit state. And so there's just no sense in which the quantum annealer, especially if we're giving it constant anneal times, needs to worry about how much time it has to go step by step through that space. It's representing the whole space, the anneal time happens and it converges to a low ground state, and there's just none of that classical kind of overhead at all. So that's why we don't necessarily shouldn't necessarily be assuming that quantum should converge like classical or should respond like classical. But the difference here, the reason it gets different here is because of those chains. And we already have experience that tells us, and other reasons to believe, that if you have problems with longer chains, the process of mapping into minor embedding the problem and then unmapping it back, even though you could be getting excellent relative errors, with respect to ground state in the physical problem, you lose some of that quality in terms of relative error when you map the problems back to the original problem space. You have to deal with broken chains, perhaps, and the sort of there are reasons why we expect some degradation of performance when we go to solving logical problems. And since we made it a point for each problem class to build the largest input of that problem class for testing here, then there's an inverse relationship in the whole test bed between n and chain length. Bigger problems, we can embed bigger problems with shorter chains, embed smaller problems with longer chains, and the quality of the quantum performance is correlating with the chain length and not with n. That's inverse to n in this particular task. But let me say, it's never terrible as well, in the sense that, even in sort of worst case scenario compared to classical, it seems to be getting pretty close to ground states. So yeah, here's more explanation. Basically, the qubits are holding the whole landscape in that one superposition state, and there's just not that same loop. There's nothing like that iteration that you have to necessarily increase the number of analog sweeps in order to explore a big enough proportion of the state space. It just doesn't work like that. And so runtime does, of course, depend on n, the anneal time to get a good quality solution. We know about the spectral gap, and you need exponential time because the gaps are decreasing exponentially slowly. But in practice, quite possibly, that's exponential in nanoseconds, and the computation, the spectral gaps could be overtaken by noise anyway, and so it's not the dominant factor when we're trying to understand how performance behaves. Yeah, and also I've come to believe, this last bullet point here, that measuring solution rank, just best, second best, third best, is more important and more informative than a measuring approximation ratio. Basically, even if we have an input that is encoded as an Ising model, and we switch it to an input that's encoded as a QPU, and we're getting great approximation ratios in one space, we can't map those approximation ratios to the other space because the constant offset in all of the solutions means you can't guarantee that any ratio with optimal is preserved in remapping. And I've kind of gotten tired of trying to do this. I just don't think that analysis, that notion of trying to preserve approximation ratio is across very diverse inputs is necessarily very helpful. Because here the approximation ratios are not too good, and yet we're finding optimal solutions. And up here, we've got excellent approximation ratios if these were optimal, but of course we don't know what they are. So that's a little side note. I need all the theoreticians in the room to come up with a better performance metric that is preserved across these embeddings and these remappings. And I think it may have to do with rank as opposed to a ratio, is all I'm saying. All right, so I think that I've pretty much said everything on this slide. And so what this means is, we have this Advantage 2 prototype. It's only got 500 qubits, but it's been sitting in the lab for half a year now, and we can see performance-wise that Advantage 2 is going to have, it's got a more, it's got a Zephyr topology, which will allow embeddings with shorter chains. It's got new technology that leads to lower noise, and there's a higher energy scale. And all of these factors show that even on the small problems that the solution qualities for Advantage 2 are much better than solution qualities for Advantage. And furthermore, when the thing gets big enough to have the 7,000 qubits, there's expected to be no substantial access time, increase in access time. So we can run these same tests again, and we'll discover that Advantage 2 is doing better than Advantage, than the current Advantage system. And also Advantage 2 is going to be able to hold larger inputs of each category. And so if we run these same tests on Advantage 2 using the identical computation times and larger problems, then the QPU solutions are going to improve. The blue lines are going to move downward. And the classical times, we know, just because we're talking about larger problems that they're trying to solve, are going to have to degrade. They're going to start later. They're going to, shift upwards because they just can't get as far in the solution space within these fixed runtimes. And also, we expect that we'll find input classes that we didn't include in the test because of this issue that they're too easy. We think we will be able to see big enough ones that at least they'll become viable to test in the next generation. So that's pretty much it. In this milestone 1, if you're looking at access times versus classical solve times, QPU is doing great. And for milestone 2, we do see it doesn't always win. It only wins about 20% of the time. But on the other hand, the places where it wins are bode well for future performance, we think, and because of these new insights we have about the two classes of solvers responding differently to the properties of the inputs. And that's it. Are there questions?
Good, thank you very much, Cathy. It's a very nice presentation. A round of applause from me on behalf of the whole audience. And yes, certainly let's open up for questions if anybody has some questions for Cathy. Either just speak up or raise your hand. No, maybe I'll start with a question then. So you said at one point that that the chain length was inversely proportional to the number of qubits, which confused me. Could you explain?
Yeah, sorry, I misspoke. Chain length in a dense problem, if you try to fit embedding, I'll try again. Embedding trades, if you have one node that's very dense, you're going to trade it for a long chain of fixed degree, really, right? And so if you have dense nodes, you need more qubits per node in your chains. And if you're using up all of your qubits in chains, in long chains, that means the original problem n is smaller than a problem that would have short chains. So
it is the number of logical qubits, is that correct?
Right. Right. Yeah. The number of logical logical qubits. The number of you can pack a small dense problem onto the chip, or you can pack a large sparse problem onto the chip. And so the number of nodes in the problem you're packing onto the chip is inversely proportional to the length of the chains on those nodes.
Understood. Okay. Something with detail, that question, I apologize. Yeah.
Oh, no worries. And there's a lot of information. It's, I'm trying to pack a lot of things, say a lot of things all at once. So
there's a question from Dennis. Go ahead, Dennis.
Yes, thank you, Cathy. Could you maybe explain a bit more what these native problems are, the ones in the blue class?
Sure. So NAT1 is a Pegasus graph. You know, it's the Ising model with plus minus ones randomly assigned to inputs. NAT7 is the same thing, except they are the weights are integers between -7 and +7, not including 0. So it's a range of weights. Corrupted bias ferromagnets are from a paper out of Los Alamos. Carlton Coffrin is one of the authors. Bias, let me see. A ferromagnet means that the the edges are ferromagnetic. A biased ferromagnet means that not all of them are. They're sprinkled with a small percentage of positive anti-ferromagnetic edges, and corrupted means that the nodes have biases, small random biases. Some of them do, and so biased ferromagnets and corrupted problems are in this Lannel paper, and there's also a paper, deceptive quantum annealing, deceptive step towards speed up by Helmut Katzgraber, that also introduces that notion of bias and corruption in inputs. These tile problems are from an early paper that basically takes, I think, takes the whole graph. It was originally proposed for a chimera graph. It takes the whole graph and makes these little square tiles, and so you sprinkle them all over the graph, and they're frustrated with respect to adjacent tiles in a certain pattern. And frustrated cluster loops were proposed in a D-Wave paper where they're like cluster loops. They're like the clusters of Google and the frustrated loops of some other paper, but they're frustrated cluster loops. Is that
okay? Great. Yeah, thank you very much.
Yeah, I can definitely send you the papers if you.
Yeah. So, have you written that up somewhere already, or is that like?
There's a draft on archive, and the paper's in submission.
Okay, very good. Yeah, I guess I'll find it. Thank you very much.
Yep. I can send you the more recent submitted draft in about a week if you send me a prompt.
Oh yes. I guess we also have an email thread open still. I think I'll just get back to you. Thank you very much.
Daniel SZ has a question.
Yes. Hi, thank you very much for this talk. I got the intuition, I don't know if I'm correct, that basically for very large samples and short times, the quantum processor performs better, but if we give it larger time, then the classical beats it. Could we construct a hybrid solver which beats everything if, say, we run first the quantum processor on the problem, just to have a good starting conditions that we put in the classical? Then would that beat like any normal classical solver? Would this make sense?
Any normal classical solver. I don't think I want to claim that we're going to beat things that we haven't tested. I will say though, these are pretty much in terms of fast inner loops. I mean, we pretty much have everything I can think of that might be a reasonable candidate here. So yeah, I think in principle it's possible. The problems with that kind of approach. So you imagine, you line up a bunch of cores, each core, one of them's quantum, and each one's solving the problem, and off you go. You kind of have to wait for all of them before you know which one's best. And so it's not really essential the case that parallel speed up means, I suppose, it kind of depends on how you look at it, I guess, but yeah, and I personally think that it's not really about does quantum beat classical on everything. I mean, the idea that, some problems are better for this approach and some problems are better for that approach. It's completely wicked hard to know in advance which solver is going to work for best input, for which input. We have a whole no free lunch theorem that tells us that. And so, actually setting these things up and just letting them run in tandem, I think is a good idea for a use case, and not trying to figure out in advance. And as long as the quantum processor can make contributions and hold its weight, then, it's done its job. We're never going to be able to claim that quantum is better on all the inputs. I mean, we know that the easy inputs are always going to be solved faster than 20 milliseconds, 15 milliseconds. So yeah.
Okay, thank you.
Any other questions? Maybe I'll ask another one then, if I may. So I guess my go-to metric, and clearly I'm much less adept at benchmarking than today's speaker, but my go-to metric would be something like the median time to solution, and plot the scaling as a function of problem size, and then see how they compare. So that's a perfectly good metric.
Yeah. So
what are the essential advantages? Why is this better, worse, different from time to solution scaling?
So time to solution. Let's just make sure we're agreeing on our terms here. Is time to achieve time to find an optimal solution, right? That you have somehow by independent means know to be optimal, right?
Okay,
and that's perfectly fine. As you know, there's plenty of benchmark work and performance analysis being done in that regard. However, as far as use cases and applications, most of, I would say, I mean, I actually counted presentations at our user group meetings, at least 75 and maybe 80% of the actual business applications. These are not people that are waiting for certified optimal solutions that need, what they have is a use case that says, here's how much time I have to get a solution. The taxi dispatch problem, I'll wait a half a second and then, the taxi's not going to wait a day and a half. And so a lot of the actual applications are more about what's the best solution you can get in a fixed time space. So this is, I think, more faithful to what we think of as the user experience, to look at it this way. And indeed, there's a long history in optimization research about evaluating problems, evaluating solvers from this approximate solution point of view. So it's, I think, a better match to our use case. And the fact is, everything we've seen suggests the quantum solver, while it can have trouble getting all the way down to ground state because of the effects of noise and control errors, it is just wicked fast at getting to near optimal states. And that fundamental distinction in performance is not part of classical, you don't see it if you're just looking for win or lose. Did I find it or didn't I find it? And so the fact that the solver does so well at that task, and that it's so important to our user base, I think, are the main reasons that we're developing, looking at this approach. And let me say more for the theoretician. It's quite possible, and I don't think these two things are inconsistent, that the idea that the quantum processor might need exponential time to get to ground state. And it's probably not going to get there by multiple samplings. I mean, you're just sampling from these are low, these distributions have skinny tails, and, get it converging from sampling, we know is like the worst possible way you can converge. And so, but the physical limitations right now and the way it's deployed say, well, you can't anneal for more than 2000 microseconds anyway. So you don't even have the capability in the machines were deployed to run for 1 million sweeps, or the analog of running simulated annealing for a second or 5 seconds. So it's always going to have really short computation times in that sense, I think. But I don't think there's any consistency between saying it takes exponential time to find a ground state, and it can very quickly find something within a certain approximation of ground state. It could be, effectively, I can't say this with a straight face, but it's given all these overheads, it's constant time. It's been a half a second computation time since I started benchmarking these things 10 years ago. We haven't increased the quantum user experience of computation times in 10 years, even though the system has gotten, 10 times bigger, 500 to 5,000 variables. So, so it's like the classical approaches to performance analysis don't apply or work differently. And so it's also just about, trying to evaluate what it does rather than evaluate how well it does what classical does, I guess is, to my mind, the difference. It was a long-winded explanation, but I apologize.
I get the general concepts, which is fine. Good. Well, if there are no more questions, let's thank Cathy again for a very interesting presentation. Lots of thought-provoking results. Round of applause on behalf of the members of the audience. And look forward to seeing you all at next week's seminar before the August break. Thank you, Cathy. Thank you, everyone, for coming.
Yep. Oh, thank you very much.
Bye-bye.